Good evening, everyone. Welcome to AS Online. So, in the last session of this SSC JE related, we have covered transformer and induction machines related questions and some important points in that. Okay. Now, in the today's session, we will see the remaining part, that is DC and synchronous machines related some questions and some important points related to that. Okay. Now, let's see. First question from DC machine here. The highest speed attainable by DC shunt motor is dash. DC shunt motor, highest speed is how much? So from the options, if you read here, much higher than no load speed, much lower than no load speed, and ideally infinite and equal to no load speed. So what is the speed? If you see the characteristics of DC shunt motor, particularly speed versus load, speed versus armature current, it will be like this. See here. Speed versus armature current or load, speed versus current. Under no load condition, what is the speed of a shunt motor? It is a finite speed only, not like a series motor, dangerous high speed. Okay. Under no load condition means current is almost zero. This is no load condition. At that time, the speed is some finite value, and after that, this is the no load speed. But whenever load increase, current taken by motor increase. When current increases, definitely the speed of the motor, as load increasing, speed of the motor slightly decrease. So this is the variation of speed of a DC shunt motor as load increases slightly. Some 30, 40, 50 RPM in that range, speed will drop, no load condition to full load condition. So what is the maximum speed or highest speed here? No load speed itself highest speed, not more than that. So after that, speed decreasing. So no load speed is the higher speed of the shunt motor. But if you take series motor, what is the highest speed of series motor? That is under no load condition, it rotates at dangerously high speed. That is ideally infinite we take for series motor it is. But right now for shunt motor it is asking here. That's why the no load speed itself, the highest speed of the DC shunt motor. Clear? Next question. Next question. See this question. Load characteristics of a DC shunt generator is determined by dash. So from the options, which one will be correct? Check it is. The load characteristics of DC shunt generator is determined by dash. See the next question. The load characteristics of DC shunt generator is determined by dash. Check it once. Tell me what is the answer for this. Yes, welcome to ACE Online. So little technical issue, that's why it is delayed. So now see here, in the last session we have seen in the first session regarding transformer and induction motor related questions and important topic points in that. Now let's see today in second session, the remaining whatever is there DC and synchronous. So in that we will cover some previous questions and also we will look into important points regarding the same questions. Let's see that. The first question here is, this is the highest speed attained by DC shunt motor is dash. So we know shunt motor is a almost constant speed motor approximately, and no load condition it will have a finite speed like this. This is the no load speed, finite speed it is. But whenever load increase, slightly the speed of motor decreases. As load increasing, the speed of the motor slightly decreases, just like induction motor. 30, 40, 50 RPM will decrease here. Okay. So what is the highest speed in this here? The highest speed is dash. Yes, the no load speed itself the highest speed of the shunt motor. No load speed itself highest speed. This is equal to no load speed. Okay. Let's see the next question. The load characteristics of a DC shunt generator is determined by dash. Load characteristics of DC shunt generator. You can see the options once here. See the options. Load characteristics. Generally it is drawn between which two parameters? Terminal voltage and load current. V versus IL. We draw this one like this. V versus IL we draw. Terminal voltage versus load current. Now, in a shunt generator, what is the voltage under no load condition? Rated voltage or not? Yes, rated voltage only. So, whenever load on generator increase, its voltage slightly decrease due to some voltage drops in generator. So, what are the voltage drops we have? One is resistance drop. Every generator will have this commonly resistance drop due to resistance of winding. And another one, armature reaction drop. So due to armature reaction, one of the effect is demagnetizing effect. So due to demagnetizing effect, some flux will reduce, voltage will drop there. Now at the same time in shunt generator particularly, so like this we get the characteristics, voltage drop. This is no load voltage, no load. So no load voltage it is dotted line. From here voltage drop. So this voltage drops. What are the voltage drops are present here? So these voltage drops are, one is resistance drop and reaction drop, and one more drop will take place in shunt generator is drop due to field current. Because if you see the diagram, shunt generator diagram, this one. This is load connected here. So whenever this load increase, load current also increases. And here we have terminal voltage. This voltage keep on decrease slightly. As this voltage decrease, what is the field current? ISH equal to V divided by RSH. Whenever this terminal voltage decreasing, the field current also drops here. But you take a separately excited generator, their field current will not drop. Field current is constant 100%. But here field current also reduces. So drop due to field current also there. So one is armature resistance drop and one is armature reaction drop, which is demagnetizing effect, and another one is drop due to field current. Now if you see here the options, voltage drop in armature resistance only given, so this is not correct. Voltage drop due to armature reaction and voltage drop due to decreased field current. Field current will decrease, and voltage drop due to armature resistance. And if you see one more here, fourth option, what is there here? Voltage drop due to reaction, voltage drop due to decrease in field current, and voltage drop due to resistance and field resistance also given. Field resistance we no need to consider, because in the previous diagram drop is due to resistance, armature reaction and field current drop only, because as field current decreases, flux in generator decrease and some more voltage will decrease. So these three only, but not field resistance, because that loop is different. No? Field resistance we no need to consider. So option is B here, option B correct. Okay. Next question. See this question. The speed torque characteristics of a DC series motor operating from a constant voltage supply is dash. Speed torque characteristics of DC series motor. So if you know one point, you can answer easily this one. What is the speed of series motor under no load condition? Dangerous high speed. No load means torque is almost zero here. This is the no load condition. At no load, what is the speed of series motor? Dangerous high speed it is. And if you see the remaining, there is some fixed speed, zero speed, zero speed. So this is wrong. So the answer is option C directly. So no load condition, the speed will be dangerous. So this is the speed torque characteristics of series motor. Next. See this question. Try to answer simultaneously. For a 6-pole DC machine with wave wound armature, the number of brushes required is dash. Tell me. Wave connection is given. So for wave wound armature, number of brushes, how many brushes required? So we have some important differences between lap and wave winding. So when it is wave connected, how many brushes? Remember, only 2 brushes for wave connection. But for lap connection, the number of brushes depends on poles. Okay. So for wave connection, it is always fixed 2 brushes required. So option A for this. And if it is lap connected, remember this, the number of brushes required is equal to poles it is, number of poles. Next one. Two DC machines, 500 kilowatt each, are tested by Hopkinson method. Hopkinson test it is. The power input would be dash. Hopkinson test. So in Hopkinson test, how many machines required? 2 identical machines required. Now in that, what is the other name of Hopkinson test? First, yes, regenerative test we call. So in Hopkinson test, with proper procedure, we can get a regenerative action in that. Once regenerative power or regenerative action started, the power taken from source will reduce by the 2 machines. So out of the 2 machines, one is behaving as motor and other is behaving as generator. So as it is regenerative test, it won't consume so much power. Regenerative, because suppose motor is there. What is the input of motor? Electrical. And generator is there. What is input of generator? Mechanical input. So motor will supply mechanical input to generator and generator will give whatever electrical power is developed to motor back. So they will exchange their powers. But it will take a small power only just to meet the losses in these 2 armatures or 2 machines. Very small losses will be there. No, losses generally not beyond the capacities of that machines. So if you see the options here, each one 500 kilowatt. Then how much power input required under this condition? 500 kilowatt, between 500 and 1000 kilowatt, none of this. So tell what is the answer? Yes. So it is none of these. Why? Because small power, it may be some 20, 30 or 5% like that approximately. But not this much, no? 500 kilowatts is capacity. That much we don't give. Just to meet losses in the machine and for field windings we give supply. But not for this, okay? But not this much of power we supply in this method. That is the advantage of Hopkinson test. That is, we need to supply only a small power just to meet losses in the 2 machines. Remember this. Next question. In a DC machine, how are the commutating pole winding connected? What is this commutating pole? If you remember interpoles, we use to reduce the effect of armature reaction, and also we use same interpoles to improve commutation. That's why as these interpoles improving commutation, we call these poles as commutating poles also. Interpoles only it is. Commutating pole nothing but interpoles. Now these interpoles are electromagnets, no? That's why that interpole winding required here. Now where that interpole winding connected? Remember, interpole winding always connected in series with armature. Okay, interpole winding in series with armature winding. Next question. A 4-pole lap wound DC generator has following details. So there is flux here, speed given, number of armature conductors, generated EMF. So it is a direct question from EMF equation of DC generators. What is the equation? The EMF induced in a generator is Z phi n P by 60n. Now all are available here, substitute directly. Z is the conductors, phi is flux per pole, and speed and poles A. Capital A is the parallel path which depends on the type of connection, lap or wave. So it is given lap connected A equal to P. So you can cancel A and P here because A equal to P for lap connection. For lap connection, parallel paths equal to poles. Then Z is how much? 440. Flux also there, 0.07. Speed is 900 RPM divided by 60. Now if you simplify, you will get 462 volts it is. Okay, 462. Check which option. Option C is correct. 462 volts. Direct question from EMF equation. Next one. Next question. Lap winding is preferred for dash. So this is very regular questions regarding lap and wave windings. Definitely one question will be there every year. Lap and wave winding differences, you should know well it is. Now lap winding we use for what? Remember, lap winding we use for low voltage high current purpose. Low voltage high current. And wave winding we use for high voltage low current purpose. High voltage and low current. Now right now it is lap winding they asked. Low voltage high current. Low voltage high current. This one, option C. Next question. Next one. See this. During plugging, external resistance is also introduced into a circuit to limit dash. So when we apply plugging is, what is the plugging? One of the braking method, electrical braking we use is plugging method. So in plugging, we add external resistor. Generally in resistance braking we use resistor, and plugging also we use resistor. Why that resistor we are using? To limit dash. Current and voltage both, none of this. Which one we have to limit? During plugging, as voltage across armature is additive, current will be very, very high. If you don't add this external resistance, as it is high current, it may damage the entire armature winding. That's why to limit that current, we are adding that resistance. Okay. So braking resistor we call RB it is. By adding this resistor, current will reduce. Next. Try to answer this. The waveform of armature MMF in DC machine is dash. Armature MMF waveform. Answer this. Armature MMF shape. So we have some shapes here. Armature MMF, armature flux and main flux. Okay. And resultant flux. Mainly armature MMF shape and main flux shape important. What is the shape of main flux in DC machine? Remember, the shape of main flux in DC machine is flat top or trapezoidal shape. Flat top or trapezoidal. And what is the shape of armature MMF? Armature MMF shape is, remember this, triangular shape it is. Having the peak of the triangular along interpolar axis. Remember this. Shape of armature MMF is triangular. So they are asking MMF here. So the shape is triangular. Next. See the next question. In a 4-pole, 20 kilowatt, 200 volt wave wound DC shunt generator, the current in each parallel path is dash. Generally, how many parallel paths will be there for lap and wave connection? That point you should know first. So for a simplex winding, when we use, the number of parallel paths in lap connection equal to number of poles. But in wave connection, the number of parallel paths always fixed, they are 2. 2 parallel paths will be there. And here they given 20 kilowatt, 200 volt wave wound DC shunt generator. But here anyhow field winding resistance nothing given, so directly I am taking only armature anyhow, armature I am taking, but given it is shunt, and how much load is connected? Load connected is power rating given, so let us take the full load capacity itself directly, 20 kilowatt power, and voltage is 200 volts. Then what is the current here approximately? 20k by 200, how much it is? Yes, 100 amperes. This is the load current, and here field current is there, and here armature current is there, and internally how many parallel paths will be there inside? 2 parallel paths will be there. Total armature winding divided into 2 parallel paths. Now current will come from these 2 parallel paths finally to the load. 100 amps is load current. Then what will be the armature current? Actually ISH required, but assume that it is generally field currents are very small, 1 amps, 2 amps. So let us neglect that. Okay. Then approximately IA also 100 in only. Then as it is 2 parallel paths, current equally divides here 50-50. So current in each parallel path they are asking. So approximately it is 50. Okay. So from the options, option D is correct. Next question. Next question. This is from starter. Read the question. Why is the hold-on coil connected in series with shunt field in a 3-point starter of a DC motor? So we connect holding coil we call, or hold-on coil, connected in series with shunt field winding in a 3-point starter of a DC motor. So why we connect? And what is the advantage of that? What happened? See here, options given. To disconnect supply when the motor is in normal operation. When motor is in normal operation, we no need to disconnect. So this is wrong. To prevent the motor from running away in case of open field circuit. Suppose you take shunt motor. Whenever shunt field winding got open circuit, what is the speed of shunt motor? See here. So motor is rotating. By drawing some currents, it is rotating. We know that from speed relation, speed inversely proportional to flux. Okay. Now when there is a field current, there is rated flux. Motor is rotating at some rated speed, normal speed under running condition. But suddenly when field got open, field winding got open due to some problem in that, then what is the field current? 0. As field current 0, flux becomes 0. So if you consider this relation inversely related, now the speed of motor may become dangerously high speed. So going to high speed, so motor may damage here under this condition. But as we connected hold-on coil in series with shunt field winding, as field winding open, now there is no closed path. No? That means what is the current in holding coil? 0. Current in holding coil becomes 0. As current is 0, now that holding magnet, so you should have proper idea first about starter. So we have one holding magnet here, that is an electromagnet, which holds the handle attached to it. Because it will attract the handle finally when we start from off to on position, it will attract, and this magnet holds that handle continuously in the on position. But whenever this field got opened, what is the strength of this magnet? 0, because no current is passing in that magnet or holding coil. Because of that, that magnet becomes completely zero field, means demagnetized simply. Then it cannot hold the handle. Then there is a spring at the bottom of the handle. That spring pulls the handle to off position. So motor is protected from that abnormal operation of motor. Means sudden high speed it may attain, otherwise if it is not connected due to this reason, flux is almost becoming 0, speed is dangerously high speed. But as it is connected, automatically it will prevent the motor from running away in case of open field circuit. Whenever field open, it will protect. So option is B here. Okay, next question. Next one. Now let's see some questions from synchronous machine. See the question. Zero power factor method for an alternator is generally used to determine dash. Zero power factor method, efficiency, synchronous impedance, voltage regulation, all of this. So why we use ZPF method? If you remember voltage regulation methods first, what are the voltage regulation methods we have? 4 methods we have. What are that? One is ZS method, also called EMF method, it is synchronous impedance method. Second, MMF method or ampere turn method we call. And third, ZPF method, also called Portier method. And one more is ASA method, American Standard Association. So by using these methods, we can find practically the regulation of alternator. So ZPF method is what? To find voltage regulation, we use this. Next question. Next. See this. Tell me the answer. The pitch factor for a full pitched winding of a synchronous machine is dash. Pitch factor. What is the pitch factor of a full pitched winding? You should have some ideas here. Full pitch, short pitch. As it is full pitched, what is the pitch factor? 1 only, no? Because what is the pitch factor equation? Pitch factor is cos of alpha by 2, where alpha is called short pitched angle. How much angle the coil is short pitched? So that depends on slots. 1 slot is short pitched or 2 slots is short pitched. Okay. But right now here full pitch winding given. Full pitch means alpha equal to 0. Means we have not short pitched. That's why alpha is 0. No short pitch angle. That is, as alpha is 0, what is cos 0? 1. Pitch factor is 1 for full pitch winding. Next question. Next one. A synchronous motor can be used as synchronous condenser when it is dash. So when a synchronous motor behaves as a condenser or capacitor, so when it will behave? Overexcited generator behaves as inductor, but overexcited motor behaves as capacitor, which operates at leading power factor always. So overexcited synchronous motor always operates at leading, so it can be used as a condenser or capacitor, overexcited case. So answer is option A for this. Okay, next question. Next one. See this question. If a 10-pole 25 Hz alternator is directly coupled to and is driven by 60 Hz synchronous motor, then the number of poles in a synchronous motor are dash. Try to find out this. 10-pole 25 Hz alternator directly coupled and driven by synchronous motor, because alternator required a input, no mechanical input required, generator required a mechanical input, and that mechanical power whatever is required, that is supplied by this one only, synchronous motor. But for synchronous motor it is operating at 60 Hz, but its poles not given. So what will be the poles for synchronous motor? So very simple. We know that alternator should rotate at synchronous speed, and also we know synchronous motor rotates at synchronous speed only. Synchronous motor rotates only at synchronous speed due to magnetic locking condition. And given here 10-pole 25 Hz alternator. For alternator, what is the synchronous speed? Calculate. 120 F divided by P. This is 10-pole 25 Hz. So here we get 120 into 25 divided by 10. How much it is? Calculate. What is synchronous speed? So we get 300 RPM. 300 RPM it is. This is the synchronous speed of alternator. That means the mechanical input, whatever the rotor we are rotating, that one is rotating at synchronous speed. Now same synchronous speed, 300 RPM. Now synchronous motor frequency given that 60 Hz. For synchronous motor, the synchronous speed only it rotates, that is 120 F divided by P. It's the frequency given but poles not given. And what is the synchronous speed of synchronous motor should be? Same as alternator speed, 300 RPM. So same speed we take here, 300, 120. Its frequency is 60, synchronous motor operating, and poles of motor unknown for us. If you calculate the number of poles, we will get 24 poles. Okay, check the value. 24 poles we will get. Clear? Generator driven by synchronous motor. So generator poles and frequency given. It is generating. That means the rotor also rotating at same speed. Rotor speed means that is synchronous motor speed only. That rotor is driven by synchronous motor. That's why we equated 300 to this. Poles we got. Next. The reactive power generated by synchronous alternator can be controlled by dash. See, in an alternator, we have both active power and reactive power control. If you want to control active power of alternator, which one we have to change? And reactive power of alternator, which one we have to change? Remember, if it is required to change active power of an alternator, we need to change its mechanical input mainly. Mechanical input or turbine we have to change. And if you want to change reactive power supplied by alternator, then we have to change mainly which one? Excitation of alternator. Excitation means flux we have to change. So remember, here it is asked reactive power of generator we need to change or control. Then which one we have to change? Field excitation, not the speed, not the terminal voltage, not the prime mover input. Whenever prime mover input changes, active power changes mainly, but excitation will change reactive power. So answer is excitation. Next question. Next one. Read this question. If excitation and terminal voltage of a synchronous motor are kept constant and load is increased, okay? Excitation constant and load is increased here. The load on synchronous motor increased, load increases. See, majority of questions in synchronous, we have from synchronous motor topic only. In SSC JE, most of the questions are there from synchronous motor topic. Compared to other topics of synchronous machine, from synchronous motor, we have majority of questions. Now see here, load increases. Then what happens? From the options, try to guess which one is correct. Armature current decrease. See, simply load increase or load decrease means current proportional to load always. That may be generator, that may be motor. Okay. So load increase means current should increase. Now you check which is the current increase. Here decrease given, wrong. Increase is there and here also increase is there. So out of the two we have to consider. Armature current increase and power factor becomes more leading. Next, armature current increase and power factor becomes more lagging. So what happened here? See, basically synchronous motor are designed to operate at which power factor? Synchronous generators are designed for operating lagging loads, are designed to operate lagging power factor loads. But synchronous motors we design generally to operate at leading power factors, leading power factor. So leading power factor means it is over-excited motor which is highly stable. Over-excited machine always highly stable. So it is designed for leading, but whenever we keep on increase the load, slowly its power factor becomes lag. Means leading is stable, when it is comes towards lagging, slowly becoming unstable it is. So remember, armature current increase and power factor slowly becomes more lag. Means it is entering into unstable, that is only, no? For any motor, if loads keep on increase, finally they may become unstable. Okay. Next. Next question. See this question. In a three-phase synchronous motor, if the direction of its field current is reversed. Now tell the answer for this. In a three-phase synchronous motor, if direction of field current is reversed, then winding of the motor will burn, motor will stop, motor will run in the reverse direction, motor will continue to run in the same direction. Tell me what will be the answer from your side. In a synchronous motor, field current, direction of field current is reversed. How to reverse field current direction? First, suppose this is synchronous motor. Salient pole, synchronous motor. Stator given three-phase supply and rotor is having DC supply, field winding, excited with DC. And with some mechanism we start the motor, because actually synchronous motor not self-start. So we use the methods here is mainly we use damper winding starting or auxiliary winding starting, like the auxiliary motor starting and damper winding starting we apply. Now here anyhow motor is rotating. Okay, now the field current reversed. Direction of field current is reversed. How to reverse? See here, when it is plus and minus, field current will flow like this. If this is the field current, no, by applying right hand thumb rule, flux is upward direction here, means here we have north pole, here we have south pole. And assume that with the given three-phase supply, RMF is rotating in clockwise at synchronous speed. Means stator poles are rotating at synchronous speed in clockwise direction. And initially this is the field current, here north and south. And as RMF rotating clockwise, these rotor also will rotate clockwise finally due to magnetic locking condition here. Rotor is rotating. Now let us change direction of field current. How to change? Now made it is positive and this is negative. Field current reverse. Whenever field current reverse, so here field current like this and flux will be down, means here north will come, here south will come. Poles will interchange. Then in which direction? What happens? So from the given options, if you see here, motor will stop, or winding of motor will burn, or motor will run in reverse direction, or motor will continue to run in the same direction. Answer? Yes. Answer is option D for this. It will continue to rotate in the same direction. Why? Because even the field current is reversed, poles will interchange, no doubt. But in which direction RMF is there here? Clockwise. Whatever the direction of RMF is there, stator RMF, in the same direction rotor will rotate always. So even if you change the direction of field current here, there is no use. It will continue to rotate in same direction. Remember this. But when synchronous motor direction we can change. Suppose I need to change the direction of synchronous motor. Then what I need to change here? I need to change this three-phase sequence. Supply sequence we have to change. Or interchange any two supply terminals. Sequence will change. Then RMF immediately reverse. But rotor immediately will not reverse. It has to stop. Again we have to start it using damper winding starting or auxiliary motor starting. Okay. Next question. Clear? The answer is the motor will continue to run in the same direction. It won't reverse. See this question. An alternator has 9 slots per pole. Okay. What is the value of pitch factor if each coil spans 8 slot pitches? Answer this yourself. Answer required. How to form poles? So poles means directly by right hand thumb rule we can see initially this is the rotor. We are giving excitation, no? Based on that poles will form. This is the field winding. Suppose supply given like this, DC supply, positive, negative, and this is the current direction. Now whenever current moving in direction, how to find the poles here, polarities? By right hand thumb rule. This is current is circulating. 4 fingers indicates current, thumb indicates flux direction. This is the 4 fingers and flux is coming upward direction. Flux moving in this direction. That means this is inside the magnet, south to north always. And externally north to south. This is the path of flux. But whenever we change direction of field current by changing this field polarities, poles will interchange just. But direction depends on RMF direction. What is the answer for this? Answer. In an alternator we have 9 slots per pole. Okay. What is the value of pitch factor if each coil spans 8 slot pitches? 9 slots per pole. Slots per pole how much? 9 are there. Slots per pole is 9. So from this calculate slot angle. What is the slot angle formula? 180 divided by slots per pole. 180 divided by slots per pole is 9, that is we get 20 degrees it is. Slot angle it is. This is slot angle formula. 180 by slots per pole. 20 degrees we got. And here given the coil span is 8 slot pitches. Coil span we indicate with the letter beta. Coil span given that beta is 8 slot pitches, means 8 slots they are simply. 8 slots. So one slot angle we have. Then for 8 slots, what is the coil span? 8 gamma. Then how much it is? 8 into 120. 8 into 20. 8 into 20 degrees. That means what is the angle total? 160 degrees. This is beta. Coil span it is. And we know from short pitch winding concept, the sum of short pitch angle and coil span must be 180 degrees. Alpha is short pitch angle and beta, alpha plus beta must be 180 degrees. And from here what is alpha? 180 minus beta, that is 20 degrees. Beta is 160 degrees. So this is the short pitch angle alpha 20. Then what is the pitch factor? Kp is cos alpha by 2. Cos alpha by 2. Alpha is 20 degrees, no? Then alpha by 2 means cos 10 degrees we get. Kp, pitch factor is cos 10. So anyhow, the options also in terms of cosine. No need to find this value. Right. Cos 10 degrees. Option B is correct. Let's see the next one. See this question. Which of the following statements is false in association with synchronous motor? So many times there are questions from synchronous motor. Try to answer this one. Which is the false statement here? They are asking which is not true or which is the false. You can see the first option. Synchronous motor is highly suitable for low power output below 40 kilowatt for medium speed range. Okay. Second option. Synchronous motor is used in constant load drive application. Voltage regulation can be done using synchronous motor. Yes. We are using synchronous motor as a condenser to change the voltage levels in the transmission network and all. So we can do the voltage regulation by using this. And synchronous motor is expensive for low power output application. So what will be the false statement here? What is the false? First one point we discuss generally for synchronous motor is synchronous motors we use, most of the motors we are using what? Induction. But where we use synchronous motor? Remember, synchronous motor we use mainly for low speed and large power applications. Low speed and for large power applications, synchronous motor are suitable. Because in low speed region, generally synchronous motor, whatever the speed it is, rotates at synchronous speed. Okay, synchronous motor 100% synchronous speed only rotates. But you take induction motor generally, compared to synchronous motor, induction motor maintenance is less, cost also less, because induction motor doesn't require the two excitations like synchronous motor. We use stator supply and also DC supply to rotor field. So like this not needed, no, for induction. That's why most of the times we use induction only. So for high speed applications and all, induction. But for low speed, induction motor not suitable. The reason is, induction motor speed is almost constant speed, because if you consider 4-pole case, what is the synchronous speed for 4-pole? 1500 RPM. Then no load speed of induction motor will be very near to synchronous speed, let 1490. And whenever load on induction motor increase, no load speed of induction motor is 1490. Whenever load of that motor increases, slightly speed drop, some 30-40 RPM drop. So out of 1500 RPM, that 30-40 is negligible there. So approximately we treat it as a constant speed motor. But in the low speed, like 300 RPM in this range, if you use induction motor, here also the speed of induction motor reduces by same 20-30 RPM. Now what is that 30 RPM in 300 RPM? 10% it is. But previously for 1500 RPM, that 30 is negligible, but not negligible here. That's why in low speed, whenever we required a constant speed, then induction motor is not preferred because it cannot maintain constant. It is variable now here. That's why synchronous motor we use for low speed and for high power applications. But if you see first point, this is wrong, no? Synchronous motor highly suitable for low power and medium speed range. It is not suitable for low power. Low power it is costliest. Induction motor is best and for this medium range speed also. And the fourth option, if you see synchronous motor is expensive for low power. So this statement is correct. This is wrong here. Okay, means they are asking anyhow false statement. No? So our answer is here option A. Next. See the question. This is on hysteresis motor. Consider the following statements about working of hysteresis motor and choose the suitable combination of correct choices. Read the statement here. First one. The stator of hysteresis motor has main winding along with auxiliary winding. Yes. Hysteresis motor will have the stator similar to single phase induction motor only. However, we have main winding, auxiliary winding, same centrifugal switch, same as it is will be there here also. Stator is same. Next, when the stator winding is fed from single phase supply, it produces a synchronously revolving magnetic field. Yes. Single winding induction motor cannot produce a proper rotating magnetic field. It is developing two fields, one is forward, one is backward. Single phase induction motor with single winding I am talking. So due to two fields, forward and backward, the torque at the starting is zero, net torque. That's why it is unable to start. But by placing auxiliary winding, what happens? By placing auxiliary winding, we are reducing the other field or backward field. Then only one field will be there which rotates at synchronous speed. So this is correct only. When stator is fed from single phase supply, it produces synchronously revolving magnetic field. So this is right. Next, the rotor material has low retentivity. So hysteresis loss is low. If retentivity is low, in BH loop you can see, retentivity is less. Then height of the loop will reduce. That height of BH loop will reduce. So generally for hysteresis motor, we need a large hysteresis loop area. We need a wider loop there. But if it is having low retentivity, what happens? Due to this low retentivity, the height will reduces. Then area also little reduces. So this is don't preferred. Hysteresis loss is low here. So we need more hysteresis loss. Based on that only hysteresis loss or power it is. Based on that we get required torque. So this is wrong statement. Next, fourth statement. The rotor of hysteresis motor consists of smooth cylinder of magnetically hard steel without any winding on this. Yes. In order to have large hysteresis area, PH loop area, we use a hard steel material here. A hard steel material in the outer layer, and inner layer will have aluminum frame. Just to reduce the weight of the rotor, we use it. So here this statement also correct. And no winding on this. Smooth surface will be there. So very with low noise, almost noiseless motor it is. It will rotate smoothly. Okay. So 1 is correct, second is correct, fourth one also correct. 1, 2 and 4. Option C is correct. Okay. So these are some questions from DC and synchronous. So majorly those who are attending in the previous SSC JE in the coming exam, so try to go through mainly synchronous motor, about regarding synchronous motor starting methods and why it is not starting, what is the starting torque of synchronous motor, and synchronous motor on bus bar, how it will behave. So when it will behave as a capacitor or condenser, when it will behave as a inductor. So we have overexcited synchronous motor is behaving as a capacitor. But in overexcited again, under no load condition or load condition. See, under no load condition, over-excited synchronous motor is a purely capacitive nature. No load condition. But whenever load is connected and it is over-excited, then also it is capacitive nature, but not pure capacitive nature. Resistive, RC combination we call. Power factor little bit reduces there. Okay, so power factor will change. No load condition, it will behave as a purely capacitor. And under excited motor behaves as purely inductor. And normal excited motor behaves as resistor. So it doesn't deliver any reactive power and doesn't absorb any reactive power. And also we have in synchronous motor some power equations, mechanical power and input electrical power. So these equations also we are getting questions regularly from synchronous motor. Okay. So these are some questions for today's session. Okay. So we'll meet some other time. All the best.